So can somebody tell me what is a semiconductor?
Yes, yes.
What is it?
Neither conductor nor insulator.
Okay, I need some more inputs.
Unidirectional unidirectional this is a unidirectional
Okay, let
circuit.
me write down. First person said that neither conductor nor insulator. This was the first comment, right? If I'm not wrong.
Yes, sir.
Okay, second one was unidirectional.
In some case, most of the cases unidirectional, and in special cases it's.
And also we can tune it.
Okay, the spelling is wrong. Case is CS is Any other? What is a
We can tune it. Semiconductor.
sorry?
Actually, sir, we can tune it.
Okay,
Tune it.
tunable. Okay, very good.
Semiconductor.
What do you mean by tunable?
Tunable in the sense what we want to the output we get.
So
In the
that I
sense
can
of
also do in
semiconductor.
a that I can also do in a when it's not a semiconductor. For instance, if I have a copper cable, okay, let's say
Okay.
and let's say I want a current. Let's say I know the resistance of this copper cable. Okay, let's say is 10
Yes.
ohms. Okay, and let's say I want to drive a current of 1 amps through this. So I can always apply 10 volts here. Correct. However,
Yes.
if I want a current of 10 amperes, I can always apply 100 volts here. So this is also tunable, is it not?
But sir, when we go through the semiconductor device like MOSFET, amplifier,
Uh-huh.
right? So I am saying in that sense.
Okay, ठीक है. So you mean to say current is tunable? Which physical quantity or which quantity is tunable? Is it current through the device?
Yes, sir.
Okay,
Yes, sir.
we'll see. I just showed you an example that even in that sense, current is tunable through a copper wire also. But fine, it's a discussion. We'll go ahead and we'll investigate whether to what extent is this thing true. This comment is definitely true. This comment we'll discuss a bit more. Okay. Any other?
Actually, yes, sir. Actually, sir,
Sir, is the
I have
resistivity
done
of
the
conductivity
One by
depends on
one. I can't. I am not able to see the screen, so I request you to go one by one, please.
Okay, sir.
Yeah.
Is the resistivity and conductivity depends on temperature?
That is also true for a resistor. I mean, for typical metal, you know that resistivity drops.
But at high temperature, the conductivity of semiconductor increases, whereas for a conductor it decreases.
So again, it's a difference between the two. So okay, I will say that okay, the conductivity decreases as in temperature increases for semiconductor, which is not true in case of a conductor. That's what you're saying, right?
Yes, sir.
Okay, so conductivity sigma decreases with rise in temperature. This is what you meant, right?
Conductivity increases, right?
Sorry,
Not rising.
conductivity increases for semiconductors. Okay. Any other? It's good.
at zero temperature at zero temperature semiconductor like insulator.
Okay, very good. Insulator at
Zero temperature.
T equal to 0 Kelvin.
0 Kelvin.
Yeah, correct. Okay.
Sir, semiconductor forms holes, electron pairs.
EH pairs. Okay.
Yes.
Okay, first we'll have to explain what is a hole. Does or all the people know what a hole is?
Yes, sir.
Anybody who does not know what a hole is? Okay, let me just see the chat once. Okay, ठीक है. Okay, good. Very good inputs. So, any other inputs, and then we'll start discussing them one by one.
Sir, without changing the temperature, we can change the conductivity.
Okay, without changing. Okay, so this was with temperature conductivity changes. Now you are arguing that. Okay, sorry. What's happened? Okay, so conductivity changes with respect to. Can you repeat your point again, please?
without changing the temperature, with constant temperature, we can actually.
So what changes? So what changes when conductivity changes? What is changing? See, you know cause and effect, right? There has to be a cause to have an effect. So you are saying effect is the conductivity changes. But what is the cause? What is change? You said temperature is not changing, so something else must be changing which changes the conductivity. What is that? Sorry?
Energy gap.
Energy gap. But for a given semiconductor at a constant temperature, energy gap is constant. Is it not?
Yes, sir.
So that energy gap does change with temperature, but we are talking about the temperature is constant here and still conductivity is changing. So I want to know the reason.
Yes, sir. Just the adding the more doping. So
very good. So doping is the cause, correct?
Yes.
You change the doping. This is the cause, and the effect is conductivity changes. We'll see how it does.
And the band gap vary.
Band gap varies only in case of high doping. For typical dopings, band gap does not change. That's at constant temperature again. So yes, it does change. I argue, but when doping is very high, like 10 to the power 22 per centimeter cube, 10 to the power 23 per centimeter cube, then only band gap changes. So for our purposes, we'll not go to those second or third order effects. So let's say this is EV, this is EC. So this is our typical band gap, correct? EG, right? So at higher dopings, so this will shift either up or down or slope changes. These are second order effects. Very good. Any other point?
We have two types of semiconductor, direct and indirect semiconductor.
That will come. I'm talking about, I mean, some salient features that if you see that, you know this is semiconductor. Like identifier.
Like LEDs.
Correct. That those are application semiconductors. Okay. So now I think you have given me very good inputs. Now we'll go ahead and discuss them. Okay. First point, conductor not insulator. Very good point. So this is I took from the Illinois University. So you can see that on the left hand side you have the insulators. Diamond is a very good insulator. Glass is an insulator, you know, glass does not conduct. Silicon and germanium are our typical semiconductors. On the right hand side we have the metals. Iron and copper are good conductors. Gold would be here, aluminium, and all metals will usually fall here. Okay? So this is the conductivity that we are seeing. So this is true. Semiconductors, like the first one, it's neither conductor nor insulator in the sense, okay, I'm talking about electricity here, not heat. This is, some people get confused by this. I should clarify. I'm talking about, when I'm talking conduction, I'm talking about conduction of electricity. So this is conductivity of electrons. Heat is a different matter. We are talking about electrons here. So very good. It's neither conductor nor insulator. Very good. Its conductivity lies somewhere in between. Now, any other interesting point? Unidirectional. It's not always unidirectional because we will see. We'll see the examples that in case of, for instance, diode is typical. A diode is a typical unidirectional device. It conducts only in one direction, and this is, let's say, forward. While in reverse, when it's reverse bias, it will conduct very, very less, like nanoamps of current. So it is not unidirectional in a strict sense, but for diode we can say diode is unidirectional, but there are some devices which are not unidirectional. They are bidirectional. Tunable is correct, and the answer for tunable is here in point number 7. What is tunable? Conductivity is tunable. See, gold, I don't know the conductivity of gold, but gold conductivity is fixed. You cannot change that. That's fixed by nature. We cannot, engineers, scientists cannot do much to change the conductivity of gold. However, conductivity of silicon, you see here is 10 to the power minus 4 per ohm per centimeter. These are the units. However, by doping it, we can make it go to as high as 10 to the power minus 2 ohm inverse centimeter inverse, or even higher. So it is tunable, and this is the thing that is tunable, and that is the magic of semiconductors, that their conductivity is tunable. For metals, conductivity is fixed. You cannot do anything. So this resistor, copper resistor, resistance is rho L by A. So rho is fixed for copper, fixed by nature. L and A are in our hands, but we cannot change rho. However, for a semiconductor, rho is also tunable, and we'll see how. Okay, conductivity increases with increasing temperature. That's a good point. That is true. That's a feature of semiconductors. Insulator at T is equal to 0 Kelvin. This is again a very good point. You see here, how does now I'll explain this in the next slide. This point number 5, and point number 6 we'll see in the next slide, and point number 7 has been explained. Can I go ahead now? If you have any comments?
Yes, sir.
Okay, very good. Now this I explained. Second thing is, what is the difference? So typically we want to express, this is a typical way of expressing of our material. So this is let's say for silicon dioxide. This is an insulator or a dielectric. Let's say this is silicon, and let's say this is aluminum. Okay, so what is the difference between the two? You can see that the valence band and conduction band are overlapping. What it means is that if there is any electron here, it is free to migrate here. In conduction band, it's like a highway, and this is like your parking lot. So in order for current to conduct, electrons should be running on a highway, either this direction or this direction. That depends on the electric field. If it's sparked, it's of no use as far as conduction of current is concerned. So in metals, so parking is next door to highway. So any number of electrons can go into the highway or come back. So that's why metals are good conductors of electricity. For semiconductors, this is not the case. For them, an electron has to do some effort to go to conduction band. From parking, it has to do a little bit of effort to go to the conduction band. This effort is usually provided by thermal energy. Can anybody tell me what is the formula, or what do we mean by thermal energy? Can somebody tell me? Okay, what is the band gap of semiconductor?
Sir, the energy at some temperature, for example, KT by Q.
KT by Q.
Thermal equivalent, we write it.
Very good. For instance, at room temperature, this is 26 milli electron volts, correct? If I am not wrong, or 25. You can calculate K, you know, Boltzmann constant. T, you know, you put 300 Kelvin. Q, we put electronic charge 1.6 E minus 10 to the power minus 19. And you calculate thermal energy comes out. Thermal energy is essentially at any given temperature, what is the energy of any entity, be it an electron, let's say phonon, anything. And any physical entity will have a thermal energy due to the fact that it is at a specific temperature. So this is the thermal energy which provides it a push. And what is the band gap for semiconductor? Can somebody tell me? EG for silicon, sorry. EG for silicon.
1.1 electron volt.
Sorry?
1.1 electron volt.
1.1 electron. For germanium?
I think 4.7 is
0.7.
0.7 electron volts. Usually these values are provided in your questions, but it's a good thing to have an idea. At least silicon you should know, because it's the most famous semiconductor. So now just I told you that to go from parking to highway, you need some energy. This energy is 26 milli electron volt. How much energy do you need? You need 1.1 electron volts. How is it possible? That 26, see, you need 26 you only have 26 milli electron volts, but you need 1.1 eV. Then how does electron at room temperature silicon conducts? So how does the electron leave valence band, go into conduction band? Can somebody tell? What's happening here? The only energy available is 26 milli electron volts, and we know 26 milli electron volts is the available energy. But required is 1.1 EV. What's happening? What's happening here? How does an electron jump from here to here?
So when we apply voltage,
Okay, one by one, please. Anyone, just start speaking.
We can
You are not audible.
like for the doping process. Hello, sir.
Yeah, go ahead.
Hello.
Yeah, go ahead.
Actually, for doping process, we can change the band.
No. For doping, doping does not change the band. Okay, I understand. Doping will introduce a level here or something. That's fine. But I'm talking about intrinsic semiconductor.
We can provide energy by increasing temperature or by
No, okay. Let me define. You cannot change it. You cannot change the temperature. You cannot dope. Or what else?
Light.
You cannot change the physical dimensions.
Maybe
sir, when we apply apply voltage.
Okay, also you cannot apply any
So when we
voltage.
apply voltage,
You cannot apply any voltage, you cannot provide any current.
So
This is a semiconductor piece at room temperature without unconnected to any current source, battery source, heat sink, heat source, anything. This is sitting on your table, as simple as that. What
Sir, we can use light to excite the electrons to jump.
Okay, I see. People are smart in this class.
Sir, we have distribution around 26 millivolt, we can say, because the energy is distributed statistically, so there will be some electrons that have higher energy that can go to the conduction band.
Very good, very good. So what happens is that this is the typical graph, or like yeah. So there will always be some electrons. So I have drawn an ideal. Let me go to, okay, hold on a second. Yeah, so the distribution is actually like this. So this is the energy, and on this scale is the number of electrons. We'll see when solid state physics we'll see this, but the idea is that there will always be some electrons which are, let's say this is 26 milli electron volts. There are always some electrons which will have higher energy, and only this number of electrons, only small number of electrons, let's say 10 to the power 10 centimeter per centimeter cube, or 10 to the power 8 per centimeter cube, only these will jump. So what's happening is that only very few number of cars from the parking lot of valence band will go to the highway of conduction band, and only very few cars will be driving on the highway. That's why the currents are typically lower as compared to metals. Currents are lower because fewer cars are driving, but still there is some current, and this is what we are interested in. In insulators, what happens, this gap is so huge, the parking lot is so far away from the highway, that however much energy you provide, so what happens is that in case of insulators, this plot looks something like this. This is very close to zero, like 10 to the power minus 10 per centimeter cube electrons. So virtually no electrons will jump from here to here. That's why in insulators like silicon dioxide, like Al2O3, these are insulators. We call them dielectrics also, like silicon nitride. These are very famous dielectrics or insulators. We see no current. So this is the reason, and this is the reason that we were saying here, that it's insulated at 0 Kelvin. So who is providing the energy? Temperature is providing the energy. Temperature, and this distribution is called Fermi-Dirac distribution. We'll see. I'll again go through these concepts when we do solid state physics. But just for the sake of completion, I'm telling you here. We'll again go through this. So due to the fact that the semiconductor piece, this silicon piece, is sitting at some finite temperature, non-zero temperature, and it has a Fermi-Dirac distribution, a small number of electrons will leave the valence band and go to conduction band, where they are free to conduct the current. Now, next question. Let's say I have, for some, any doubts still here? You want me to repeat something? Comment, suggestions, anything? Okay, I'll go ahead. Let me just see if any other people are trying to get in or not. No, okay, good. Okay, next. Now, once the electrons have reached here, they must conduct, right? Now, before going into that, I need to talk a bit about the type of semiconductors. Can anybody tell me what is the difference between? Okay, so let me start. There are different qualifications. One is intrinsic versus extrinsic. Everybody knows the difference between the two? If anybody does not know, please say yes. They don't know. All good here? Extrinsic means we have doping. As someone suggested in the first slide, why we do doping? So that we can tune the conductivity, increase it, decrease it, and whatnot. The second thing is that, okay, can anybody tell me a semiconductor apart from silicon and germanium? Any other semiconductor?
Gallium arsenide.
Gallium arsenide. Okay, any other? Okay, I'll tell you. Gallium nitride. Okay, these are called elemental semiconductors. Elemental, because there is only silicon is there, and that's a semiconductor. However, you see silicon, where is that? This group, silicon, germanium. group 14. However, what physicists and scientists figure out, that if we combine one element from group 13 and group 15, this compound will behave like a group 14. So what they did, the very simple thing, they picked one gallium, one arsenide. So they picked one gallium plus one arsenide. They formed a compound called gallium arsenide, and surprise, surprise, it was a semiconductor, just like germanium. The properties are different, of course, but it is a semiconductor. Similarly, if I take a one group 13 element like gallium and one group 15 element like nitrogen, so it will form gallium nitride, which is again a semiconductor. That's how we play. So these are called elemental, these are called binary semiconductors. Binary stands for two because there are two elements. These are called elemental or unary semiconductors. Right. Now somebody pointed out there is again a class direct versus indirect. Can somebody tell me what is silicon a direct band gap or indirect band gap semi? Okay, what can somebody tell me? Is silicon
Indirect.
Okay.
Silicon.
Example of a direct band gap semiconductor?
Gallium arsenide.
Gallium arsenide. Very good. What do we mean by what do we mean when we say direct and indirect? Okay. So let me draw an EK diagram. So this is energy. On y-axis I have energy. On x-axis I have momentum. This is momentum space. This is your valence band. This is your conduction band. EV, EC, and this is what we called as EG. We'll see this in solid state physics. We have a model called Ronik-Penne model. Have some people heard about it? Ronik-Penne model. Okay, even if not, we'll cover it. So Ronik-Penne, what it says is that you can treat lattice as a like this. It has some simplifications, and it says that you can treat the electron as a wave, and we know a wave has a energy, free wave has a momentum like p square, proportional to p square over 2m. So that's why this looks like a parabola. Anyways, if the top of valence band lies directly below top of conduction band, this is called direct band gap, because an electron can directly jump from here to here. However, this is your gallium arsenide. In case of silicon, however, it looks something like this. This is your valence band and this is your conduction band. So you cannot jump directly from here to here. You will go from here to here and then from here to here. This is just a small difference. It might be important. A question might come, identify this direct band gap semiconductors or indirect band gap semiconductors. We'll again go through this in solid state physics, so no need to bother if you have not. We'll go in depth there. Okay, now I'll be starting the questions. Before I start the questions, I need to ask you whether you have any doubts or any comments that you need to make right now. Please go ahead. Or any doubt of your own you have right now. That's also good.
Sir.
Yeah, go ahead.
Sir, in that silicon's graph you made just now for the silicon band gap.
Yeah.
Sir, the y-axis represents energy, right, sir?
Correct. Y-axis energy. Yeah.
What does x-axis represent?
X-axis is momentum. So I told you. Okay.
Okay, sir. So it's shifted by momentum, right, sir?
Yes. So
E,
K. So this is your silicon. This is your valence band, conduction band. So let's say electron wants to go from here to here. So it has to have, it will go through this path. So it will need this much of energy, which will be provided by a photon. Photon has energy h nu, correct? And the momentum change will be provided by a phonon. So it will have a certain momentum. Every phonon has a certain momentum. We'll see about phonons, and that's I was not going in depth because we'll see this in solid state physics. There's a good phonon concept in solid state physics. Yeah. Any other doubts?
Okay, sir. Thank you, sir.
Yeah. Go ahead. Somebody else was also speaking. Okay. Shall we start with questions now? If there are no comments. Okay. I'll start with questions. You are going to solve this problem for me. I am not going to solve this problem. Okay. Okay. How does everybody know Hall effect? What Hall effect is?
Yes, sir.
Okay. The thing is, when I look through the previous year questions, every second or third year a Hall effect question comes, and it's very scoring. It's very simple. There are just two formulas and very simple concepts. It's very scoring. I highly suggest you get yourself comfortable with Hall effect. It's very simple. I'll explain in a bit here. So what's happening is, this is a semiconductor block, okay, and a current. So what we have done is we have applied some voltage to this, okay. Let's say the voltage we have applied is VA. So because I've applied some voltage, some current, because it has some finite conductivity, so current will start to flow. Let's call this I. Now what I am doing is I am applying a transverse magnetic field. Magnetic field is going into the plane of the paper. I think X is the symbol to denote it. Now think about an electron which is traveling. So so this is positive, this is negative, so electron will be going in this direction. Current is in this direction, and electrons current is taken to be in the opposite direction. So electron is flowing this. Now focus on this electron. Now what's Lorentz force? Can somebody tell me the formula of Lorentz force?
QV cross V.
Okay, actually it's QE plus V cross V, if I'm not wrong. So let's ignore E for the time being because we are considered only here. So it's QV cross B, okay. Both are vectors. So velocity is in, so Q, electronic charge is negative, V is in negative I direction, and B is in negative K, okay. I am assuming this I, J, K. This is my coordinate system. So this will come out to be I cross K is I cross J is so minus cancel out, so it will come out to be J cap, okay. So electrons will feel a force in J cap, means electrons, rather than going this way, it will go something like this, and they will start to accumulate here. So this will acquire a negative charge. Let me change the color of my pen.
So I cross K minus J. Okay.
I cross K is minus J. This is a minus sign also due to the electronic sign.
Yes.
So overall it will be plus J. So force is in plus J direction, so electron will move in this direction. So this will acquire, and electrons will start to accumulate here. So this phase will become negatively charged, and this will become positively charged. Now we can measure this voltage, very small voltage, but we can measure, and we call this voltage Hall voltage. So if we apply a voltmeter across this, the top face and bottom face, and I measure the voltage, I'll get some reading. We call that Hall voltage, VH. So there are certain formulas. The derivations you can find relatively easy. I will not derive them. If you have any doubt, you can ask me. We will not derive this. We will directly go to the formula that we have. So we have a couple of formula. I am writing them. Yeah.
Hello, Amit. Can you more explain about the directions of magnetic field into that?
So magnetic field, you see, when we are doing an experiment, and experimentalists give some stimulus, give some inputs. So I have given two inputs to this semiconductor block. One input I have given is voltage, this. Second, I have applied a magnetic field B into the plane of the paper, into the plane of your screen, which you are seeing here.
Okay.
I just wrote them simply an electron, and since a voltage is applied, electron will feel an electric force and it will drift. So electron is moving, but there is a field also, so it will move and it accumulate here. This is a very small voltage, but it's measurable. It's a few millivolts or microvolts, but it's measurable. Yeah. Okay. So the thing is, we can, so you see, if it were an electron, it will go here, correct? In this system. However, if it was a hole, where will it go? Can somebody tell me? If it was a hole,
lower plate.
No, if the current is
lower phase.
Lower phase, correct? So we can see that electrons and holes behave differently. Why are they behaving differently? Simply because they have different charge. This Q will change the sign then, correct? So you can see that these things. So it's a good tool to see whether a semiconductor is N type or P type. What do we mean by N type? I'll go to previous slide. So let's say silicon is an elemental semiconductor. It's an intrinsic semiconductor. However, if I add some amount of, let's say, boron in it, okay, it will behave an n type. Means intrinsic means n equal to p, number of electrons is equal to number of holes. However, when I add n type, so what I'm doing, I'm deliberately increasing the value of n, so this will behave like an n type. Now we'll see in formula with more details. So now, okay, please solve this question for me. The Hall effect experiment on an intrinsic semiconductor. Remember this is not doped. Which of the following statements are correct? Okay, which of the following are correct? Hall voltage is always zero. Is Hall voltage always zero? Yes or no?
As you told that there is some voltage is necessary, so not zero.
So not zero. Not always zero. It may be zero. Insulators
not always zero. Yeah.
Insulator
yeah, maybe zero. Yeah.
Yeah. So this is wrong. Okay. We have to find correct. Okay. So this is not correct. I'll put cross here, not here. Okay. Second, Hall voltage is negative if effective mass of holes is larger than those of electrons. Okay. So here I was
depends on charge, I think.
it depends on charge also, correct. So no, here the n equal to p, since it's intrinsic, so n equal to p, correct. So the number of holes and number, so if an electron is traveling here, a hole is traveling here also, remember that. Okay, so now what, so q will be the same for both. Now the difference only will be b is same for both. Okay, let's compare an electron and a hole. Electron and a hole, q is same for both, b is same for both. I'm writing down the formula of Hall voltage so that you are able to follow it easily using formula. VH is equal to BIT over NQA. Okay, I'll explain. B is magnetic field, I is the current flowing through the semiconductor, T is the thickness of the semiconductor. This dimension is T. This is same for hole and electrons. N, this is important. This is the number of holes in case of holes, or number of electrons in case of electrons. Q and A. Okay. So, okay. So what we see here is that since usually mobility of electrons is greater than mobility of holes. This is a fact. Again, we will see in solid state physics, but just bear with me and just explain. Assume this to be true for most of the semiconductors, that mobility of electrons is greater than mobility of holes. What this means is that for electron and hole feeling same force, they will move. Electron will be able to move faster, but we measure VH at a steady state. So this is not always true. Again, this is not always true. In steady state, there will be the electron and hole will cancel themselves out. That's what's happening. Next, Hall coefficient can be used to estimate the carrier concentration. This is true. What is Hall coefficient? Hall coefficient is nothing but VH upon VH into A upon IBT. So what you take every term here. So this will turn out to be 1 upon NQ. This is called Hall coefficient. So Hall coefficient is 1 over NQ. Now, Hall coefficient can be used to find the this N is your number of holes or electrons, what we call the electron concentration or hole concentration. But since this is an intrinsic semiconductor, this is not so simple, because it has components of electrons as well as holes. For extrinsic semiconductor, this was easy, because there the electron concentration is N plus N boron, which is greater than P. This is N silicon, P silicon. So there N boron dominates P silicon, and there it's easy to estimate. But this is an intrinsic semiconductor, so this statement is also not correct. The only statement left is Hall voltage depends on mobility of carrier. This is the only statement that fits among these two. Okay, just ask me if it was too much. We'll again go through a couple of more questions and we'll come back to this. If you have any doubts here, please ask me right now in this question.
So explain the option D.
Option
D. Explain the option D. Why it is correct.
Option D. This option.
Yes, sir.
Okay. So what's happening is that okay. So the current I current I is let me recall. Current I is your, you know, dq over dt. Okay, am I correct? Dq over dt, yeah.
Yes.
So I can write okay, one second, let me add a slide. Okay, current is dq by dt, which is equal to, now current will be n times, let's say I'm considering only electrons now, so it will be number of electrons, capital N, into charge of electron upon dt. E is constant, it comes out, it will be dn over dt. Okay, now let's consider this block of semiconductor and electrons are traveling in this direction. So let's assume this dx portion. So how many electrons are there? Let's say that the electronic density is n centimeter inverse. This means n, small n, number of electrons per centimeter cube. So total, so dn would be, this is the electronic density times cross sectional area times dx. Very simple. So I'll write this. So dn is n times area, cross sectional area, times dx over dt. So this is ENA. Dx over dt is nothing but drift velocity, correct? Dx over dt is velocity. And can somebody tell me the formula for velocity in terms of mobility? It's mu e. Mobility times electric field. So this comes out to be NEA mu into E. This is I. I'll take I here, so it will come out to be J equal to NEA into mu. What is this? What is this law called? J
Ohm's law.
Ohm's law. Very good. So conductivity comes out to be, okay. Now you see in expression of current, there is a term called mobility. You see this? So if I take this back here, where was the current? So I was here, correct? I must replace this I by that expression that we derived there. So I'll write it again. So VH was BIT over NQA. I'll write I as NEA mu times E into thickness T over NQA. So you see here the mobility term survives. Can you see that? This term. Hence it depends, Hall voltage depends on mobility of carriers. That's why we take this statement. Because in this formula there's a term called, see, I'll write it again, B E mu E T over Q. This is the Hall voltage formula. B is constant, E is constant. Electric field, applied electric field is nothing but the voltage that we apply. We applied a voltage, remember, VA. So this is constant, T is constant, Q is constant. So Hall voltage depends directly on mobility. That's why option D. Is it clear now?
Yes.
Okay. We'll go to the next question. Okay, it's a very simple question. Choose the correct from the following. Come on, we do this in less than 2 minutes. Is first option correct?
No, sir.
Okay, we just saw in EK diagram which I drew, this and this. This is EV, this is EC for silicon. This is not direct. Direct means it should have been here. So this is not correct. Conductivity of metal decrease with increase in temperature. This is true. Wait.
It's true, yeah.
This is true. Correct. So this option seems to be. Conductivity of semiconductor decrease. This is false. We just discussed this in the first slide. Correct. And gallium arsenide is in that. This is also false. Gallium arsenide is, I told you, like it's like this.
Direct, yeah.
It's
You have discussed it.
Yeah. Okay. Very good. So the correct option is B. Okay. Very good. This question now. This is a very simple and simply formula based question. We have discussed all the theory that there was to discuss. So what we have a germanium semiconductor is doped with acceptor impurity. Okay. I told you that there are two types of impurities. Donor. I'll go to that slide again. So we called these impurities, group 13 impurities, donor. Sorry, we called group 15, I'll write it again. So this is group 14, 15 and 13. So we have boron and aluminium here, germanium, silicon, sorry, silicon is up there, and here we have nitrogen, phosphorus. So these are called donors because they donate electrons to group 14. These are called acceptors. Why? Because they accept electrons from group 14. So these are called acceptors. These are called donors. Okay. Now it's a germanium semiconductor is doped with acceptor impurity. This implies now it's an extrinsic semiconductor. This is no more intrinsic. Okay. So we have been given Na equal to 10 to the power 15 atoms per centimeter cube. Hole mobility, I'll write mu h equal to 1800 centimeter square per volt second. Resistivity, rho is what? Okay, coincidentally we just derived that. Where was it? I derived it, right? Yeah, here. Is it? Wait.
Yeah, sigma.
Okay. So no, wait, but we have been given mobility and this. Okay, ठीक है. Okay. Okay, we know N. N is the concentration. What is the concentration here? Na, which is given. So I'll simply put 10 to the 15. E. E we know is electronic charge 1.6 10 to the 19 minus 19, sorry. Mobility. Mobility is again given 1800. Remember, we are finding of holes. Acceptor and holes go hand in hand. Okay, if we are talking about acceptor, we must talk about mobility of holes. If it were donor, let's say it were 10 to the power 12 donor, then we talk about mobility of electrons, because in this system there are very less electrons and there are more holes. So number of electrons is greater than number of holes. So there is no point talking about mobility of holes or conductivity of holes, because if electrons will provide current of 1 milliamperes, holes will provide currents of 1 nanoamperes, and 1 milliamperes plus 1 nanoamperes is approximately 1 milliamperes. That's why when we talk about system which has acceptor ions, we don't talk about electrons. Conversely, if we have a system which has donor materials, we don't talk about holes. This is a system which has acceptor impurity, so we talk about holes. Sigma h Ne nu 1800 centimeter square per volt second. Okay, we need a calculator.
3.472.
Okay, thank you. So this comes out to be, you are allowed calculator in exam,
resistivity, right? Sir, it is resistivity that I am telling. Okay. Conductivity is 0.288.
So this is 0.288 centimeters.
Yes.
Sorry, units would be ohm inverse, centimeter inverse. Now we needed to find rho h. Rho h is nothing but 1 over sigma h. So 1 by 0.2, yeah, it will come out to be 3.47 ohm centimeter. Very simple formula based questions. We've already discussed the theory. If you have any doubt, okay, now what happens? If it's an intrinsic semiconductor, in that we have holes and electrons. So there I write sigma h equal to NH E mu h. I write sigma E equal to Ne times electronic charge times mu E. So total conductivity would be
simply sigma h plus sigma e.
No.
Oh, one by, yeah.
It's like this.
Okay.
See, the smaller one will dominate. Let's say you have been tied to a tortoise and you want to run a race. Who will determine how fast will you run? A hare and tortoise have been tied together and they have to run a race together. Tortoise will determine how fast will they run, right? Because this is the slower fellow. Always the determining factor will be whoever is smaller, and this inverse relation gives out the smaller one. This is again, this question can come, please remember. This is a very, people remember sigma h and sigma e. What happens when there is both? This happens when there is both. Please remember this. Next.
Sir, is mobility of holes and electrons somehow related?
Yes, it is related. I'll tell you how. Let's just discuss the next question. Okay, we have two more questions. Okay, this question is that only. Fine. No, not entirely. Okay, so what are electrons? So I am drawing, let's say silicon. Silicon is, can somebody tell me the 1s2, 2s2, 2p, wait, I forgot, 2p6, 3s2, 3p4, 3p3, please help me.
3p2.
3p2, okay, so this hybridizes, it becomes, so there are 4 valence electrons, correct? Now I've already drawn the shell 3, so there are 4 vacancies in silicon. This is a silicon. So what it does is that it forms bond with another silicon like this. You must have seen this figure. This is covalent bond. There is one covalent bond here, one here, one here, and one here, right? So when electron wants to conduct, it jumps from one place to another. Simple. For hole to conduct, it's difficult. What is a hole? Hole is nothing but an electron vacancy. So this is a silicon. So square is a hole and circle is an electron. This is shell 3 of silicon. So when can a hole conduct? An electron can conduct easily. It will, if you provided ionization energy, this will leave this and it will create another hole, and it will go to the highway of conduction and it will roam freely there. Hole is not so easy. For a hole to conduct, there has to be another hole nearby. Let's say there are 4 electrons here. How can this hole come from here to here? It is only possible when this electron jumps from here to here. So effectively hole has come from here to here, and it's easier to ionize an electron. It's easier for an electron to find energy to leave the electric field of silicon nucleus then, because it is a 2-step process. So electron has to leave and come here. Here electron just has to leave. That's why typically we have mobility of holes less than mobility of electrons. Typically, especially in silicon, this is true. That's why we have that. Again, this is the same question that we did earlier. Remember this, Hall voltage depends on mobility of carriers. This is the same question again. In Hall measurement, Hall voltage is negative. This is because, why is this? Tell me, we just told this. This is because of, come on, this is because of this. Because an electron, when we apply a magnetic field here and let's say a current is flowing through the semiconductor block like this, since electron has higher mobility, they will be able to come here faster, so they will accumulate here more as compared to holes, and hence we'll have a slightly negative Hall voltage. Next, this is again a numerical answer, this is again a numerical, a very simple question. This we had talked about. So again, this is the same diagram. So we have been given I. Okay, remember this is a p type. So since it's a p type, we'll only talk about holes. So we'll only talk about mu h, sigma h, and nh. We won't talk about concentration of electrons, conductivity of electrons, and mobility of electrons, because Ne is less than Nh, and we can ignore simply. Okay, so as I had told you, we had discussed a formula earlier somewhere. It was something like this. VH was BIT over, can somebody tell me what was the formula? Over NQA. This was the formula. Yeah. Okay. So VH has been given to us as, this is not, okay, where is VH? This is VH, Vy. Electric field is applied downwards. So let's say electron is traveling here. Electron will be traveling in this direction. Electron will be traveling. Current is flowing. Electron will go here. So again, I'll apply F equal to Q V cross B. Okay. Oh, electron won't be here. It's a hole. So hole will be traveling in this direction. So hole charge is positive. So this is positive. V is positive I. This is my coordinate system. I, J, K. So this is plus I, B is minus J, B is minus J, so I cross J is minus K. Okay, so force on holes will be on negative K direction. Negative K means into the plane of paper, so they will be traveling in this direction. So holes will accumulate on the back edge and this will become slightly negatively charged consequently, right? So we can see there is a small hall voltage here and this has been measured as 0.25 volts because this is the voltage that we are measuring. So this will be 0.25 equal to B is given, I is given, T is given, N is not given, and we have to determine Q. We know 1.6 10 to the minus 19. Area will cancel out, we'll see how. So, or we can use this formula. There was one more formula I forgot. This one. Yeah, this one, J equal to NEA nu into E. So we can use, or we can use this one only. So here we'll get N into A. N is the concentration of holes, in this case NH. So you can get NH from here, and then what we do is simply we know that current equal to Q times, drift velocity will be equal to current times NQA, right? So and we know drift velocity is nothing but drift velocity, so I can write I equal to NQA into VD, and we know N from this, N into A, so this expression will be here, and we know VD, we can calculate VD from here, and if we get VD, then we can get VD equal to mu into E. E is nothing but applied electric field, which is this 2 millivolts. L and L will also cancel out here. This is a fairly straightforward question. L is given actually 10 mm. A is also given, I forgot, 10 into 4. Everything is given, so you can simply calculate N from here, NH from here. We calculate NH from here, we put it in this formula, we get VD. When we get VD, we know drift velocity is equal to mu into E, and you can calculate the mobility of holes. Do you have any doubts here in this? Should I explain it again? Please
respond. Sir, how you are calculating the voltage, hall voltage, VH?
Sorry?
Sir, how we determine VH is equal to 0.25 millivolt?
That we have measured. This has been given. This is a voltmeter that has been applied.
I think, sir, what I want is how you calculated the vector notation there.
No, vector notation. Okay, I was calculating the in which direction the holes will move. Okay, I'll do that again. So Lorentz force is Q V cross B. Okay. Now holes, this is we are not considering electrons. We are only considering holes. So if current is flowing in this direction, hole will also be flowing in this direction. Okay. A hole charge is positive 1.6 e to the power minus 19. Its velocity is in positive x direction, plus I. Electric field is given in minus K. This is given. B is here. B is in minus K. This is plus. I cross K is, so the minus sign comes out, minus J. So this will comes out to be plus J. So the force on holes will be in positive J direction. Okay. This means the holes will be moving on this one. Did I calculate wrong before or now? I cross K is minus J, right? Can you hear me?
Yes, minus J.
Did I do anything wrong? I don't think I did anything wrong here. This is correct. So they will move in this. So now this will get somewhat positive. Now if you apply a voltmeter across this and this, you will measure some voltage. This voltage has been measured to be 0.25 millivolts. This is what I was talking about. Is it clear now?
Yes, sir.
Okay. and you can simply go through the formulas that we have discussed. Excuse me, is there a doubt? Is it clear, or should I do it again, because this was a bit messy?
It's clear, sir.
Okay, ठीक है. Okay, that is all I had for today. If you have any doubts, please ask me of this or any other semiconductor thing that you want to know about.
Sir, can you please rewrite the drift velocities formula?
Sorry, this question again?
Yes, sir. Drift velocity. What was the formula?
Okay, so drift velocity is defined as mobility times applied electric field. So you see, hole is drifting from here to here, correct? You can see it's drifting like this. Current is here, hole will also go in this direction. So what is electric field applied? Electric field applied will be nothing but V applied divided by length. Length is L. So this is what I mean. This we need to know. This we calculated from our current formula, the formula of current that we had.
So V applied is Vx.
V applied is Vx, yes. So it will be Vx over L. So you can substitute the values. So I'm not doing the mathematics here. My aim is to just to see, if you know how to solve a problem, you will solve the problem. You are not dumb people sitting there. It's just that only I have to do some guidance so that you reach there eventually. Yeah.
Yes, sir. I just missed the formula.
No, you are correct. I missed actually. Because it's E applied, but E applied is nothing here. The voltage is the applied, which gives rise to an electric field, and hence the holes drift. Yeah.
Thank you.
Yeah. Okay. So let me just, in the next class, what we'll be doing, we'll be looking at band gaps in a bit more detail. Second thing what we'll be looking at, we'll try to determine the Fermi levels. Okay, this is a very favorite question in GATE. Every second or third year there is a question on Fermi levels, so you should be, and it's very easy. There are just conceptually it's very easy to understand, and there is just one or two formulas, and the questions keep just change the numbers and they keep repeating. It's scoring also. Conceptually it's easy to understand, and if time permitting, let's see. And if you have, I highly encourage, if you have any other doubts of yourself, conceptual or problems, please ask. Mail me before the class if there is time. Conceptual I will definitely discuss. If there is time, we'll take problems also. Okay, right. So any other thing, any other comments, suggestions? Has the schedule been shared with you, the calendar, where
Yes.
So you knew I was going to do semiconductors. I am going to do semiconductors next week. Is that information available to you?
Yes.
Okay, good.
It is visible on the side.
Okay, very good.
Sir,
Yeah,
please make
your voice is breaking. Sorry, can you repeat?
sir, please make a program set for us, like for our solving.
No, I'm not able to understand the.
Sorry,
We talk about assignment. You just
yes.
yeah.
Assignment. Okay.
Yeah.
Please make the assignment for us.
Okay. I'll not do that. I'll tell you why I'll not do that. Your assignment, you have previous year questions with you, right? Yes or no?
Yes.
Those, see, I highly, see, whatever questions we are discussing in class, you must do it yourself, because see, I have done this question. I'm not doing this first time. I've done this. I practiced 2 times before I teach you in the class. So I've already, only on the second or third time, I do not remember these formulas. I had to go through in my textbooks, and I read a bit that what is drift velocity. Like someone was talking about the temperature, with temperature conductivity decreases. So I read that theory. I can make it, the assignments are nothing but your previous year questions. Okay, if you still insist, I'll give this suggestion to NPTEL team, and they'll do the needful. So you rest assured, we'll try to help you as much as we can. So I'll pass this suggestion to NPTEL team that students are requesting that we have some assignments. Okay, yeah, okay. And okay, I forgot one more thing. you know, you can always go to your NPTEL courses if you need some in-depth understanding. Okay, you can always search for the courses. There are different courses, so you have to be careful how much in depth you need to go. You should, and again, talk to your friends. Here you can email me and my teammates, and we'll get back to you via email. Okay, so assignments I have noted down. You have asked for assignments. I'll pass that information. Any other
Can you share email?
I did that. Okay, I'll copy and paste. 1 second. Okay, Shruti, you had asked why VX. Is it clear? Shruti, are you here? Okay, maybe she left.